My name's Mike Seplowitz. Like Ashley said, I work in deployment solutions at Bloomberg in New York. If you're looking for the slides, if it helps you, they're up on my personal website, which is very tiny, so there's only one link on that page that says slides. That's the link. So I wanted to talk today. This talk is sort of two parts. It's the story of this project that I've been working on for a little while now. And I also wanted to make sure I give you folks here something that you can take away if you want to build a tool like this yourself too. So in terms of what we're going to go through in the talk, I'm going to introduce the problem. We're going to talk about a couple of important questions that I wanted to make sure we answered. And then talk a little bit about the exploration I did before I got started. And then we'll take a detour into sort of a primer. I don't know if primer is the right word, but a bit of an introduction and tips and tricks to keep maybe you on a better path than I took if you're going to get into static analysis. And then we'll talk about attempt one. Of course, there's attempt one, there's an attempt two, and then finally some takeaways at the end. My disclaimer is that I'm not a programming language expert. I do not claim to be. I'm a hobbyist in that, so I know some buzzwords. I will try not to use them today. So by way of introduction of the problem, I joined what became Deployment Solutions a little over 2 years ago, and we really took some time to step back and brainstorm some ideas for what we wanted our ideal system to be. We wanted to deploy small changes often. We identified parts of our workflow that seemed to be obstacles to that goal, and for our team, that pointed to microservices. The slide had to come up at some point. And my colleague Pat suggested we try this not really that new language that he really liked called Go. We started small. Our microservices served only a single request. I think when we mentioned this to a Go veteran, they said we really should call them nanoservices then. But as we added more and more services to the system, it quickly became apparent that it's going to be hard to keep track of them all. So we should write documentation, right? Many of us had worked on other teams that we had. I really appreciate well-written documentation, but I know the reality is it's hard to keep things up to date. It often doesn't pan out. Do you have a centralized docs repo? Well, but then people forget to update it. Okay, so we should put all the docs in the project repos then. But then how do you read the whole thing? It's hard. It's hard to keep up with it, and that's where static analysis seemed like an interesting idea to me. If we're producing documentation or artifacts from the actual code, then it's nearly impossible to have inaccurate docs, right? They stay live with the code. So I was looking for a few different things to get out of this project. I wanted to know about the dependencies of a single service. So that lets us highlight the effects of a code change. If I put in a PR and I'm suddenly calling a new library that uses a new service, might not be exactly obvious. But if I can have a thing post in the change request, hey, by the way, this adds a new dependency, that seems like a good thing for a reviewer to know about. And then having inter-service dependencies across the whole system, we can visualize the system graph, right? We can detect cycles, which isn't necessarily 100% bad, but probably makes you think twice. And we can maybe even overlay traffic data on the static graph. So I sort of went a little quick around the term static analysis. What I mean here is that the code is static, right? We're writing programs or using tools to analyze the code in place. We're not running it, right? And this would be sort of a combination of static and dynamic analysis, if that's the right term, right? So if we overlay our traffic on the static graph that we built, we could see, well, here's a link that's not being used. Whether that's correct, you deprecated that service, or you're trying to remove the calls, or something's broken, right? So that's sort of where that came up. So the plan. I wanted to find interesting function calls. Interesting. And those call destinations would be the dependency of the service, right? And the service dependencies, we could put them together to make a graph of the entire system, how things are calling through. Finding the interesting function calls makes sense in that sort of when you look at Go and you look at the standard library, I don't know, it feels more approachable to me in that the library is fairly focused, and there's a few things we use a lot. You use certain functions to call other services, to open up resources on the system. And so if we can track these in terms of function calls, it seemed like things would fit together. So there's a few important questions I wanted to answer first. I made air quotes before. What are these interesting calls that we care about? The obvious ones when you start dealing with HTTP services, the things in the network package, NetDial, NetHTTP GET, and the client GET, right? This is a notation you're going to see in a bunch of places in the talk. When there's parentheses around things, it means that's the receiver on the left, just to clarify. But we might talk about things that are a little higher level. So not just one service calling another service, but a service relying on some other external dependency, right? Like a database, making a gRPC call, accessing Redis, putting something on or off a RabbitMQ or a Kafka message bus, right? These sorts of things. And really what we're also talking about here is just sort of inter-process communication in general. And there's another way to communicate across processes, which is to run them, right? You can run new processes. You can actually find processes that already exist on the system and then try to talk to them, or I guess kill them, send them signals. And you can open up pipes to different places too. And sort of last but not least, if you've tried to build systems that interact with sort of the very primitive data that we get is the file system, right? Opening up files. I've built systems where I built systems that for simplicity reasons, we actually just used a file on disk as like a queue mechanism between two processes so that they would be decoupled. So if you're communicating through a file of some sort, knowing when you open these files would be interesting. And again, highlighting a little bit, remember the structs in Go. Go makes the separation between the structs and the methods on those structs, right? And we don't have classes in that sort of way. So the struct itself doesn't have any behavior. So we don't need to look through those particularly. We can look for places where the structs are used either with function calls or with methods. I also need to know who are we calling, right? The people we're calling out to, whether you're calling the database or calling a service. When you're a human and you look at this, it's pretty obvious, right? I'm calling this thing. But the string probably is rarely hard-coded in your code if it's been around for a little while. You'd have a parameter that's read from a configuration or an environment variable or passed around. So it probably looks something more like this. And as a human, I can look at that and be like, yeah, it's calling my service. But it's a little dicey. It's not always going to be named that way. Maybe I use a short name. Go likes to use, the Go idiom is to use short names a lot, or short variable names, not really, really long things. So how do I go digging for this? Do I start making regexes that look for like URL or DSN at the beginning or the end of variable names? It was starting to get really messy. You also might be getting it from somewhere inside your application's config that you read earlier during startup in main or something. So I want to step back. So I do an HTTP GET, and I want to add an annotation to this line of code to explain what's going on. And this, to me, felt a lot like a comment. So I wanted to use a slightly specialized syntax to avoid false positives, but also have it feel kind of natural. And this is sort of where I settled. Doesn't have to be this way. And with the code analysis tools that we get in Go, we can also find sort of comments in the neighborhood of your code. So you don't have to necessarily jam it into the middle of a line, or you can try to help clarify things like that. The other really important question that I wanted to answer here was, which call do we mark? So I want to show a couple of examples why, if you start thinking about your test cases, or the use cases rather, it starts to get a little funny, but I think it makes sense eventually. You can have a direct call. That's super straightforward. you could have what I'll call a specific helper, right? And if you look at its name, it's only going to call one place. It's very targeted, right? Here, now I'm calling my helper, which then calls HTTP GET. HTTP GET is our interesting call, right? You can have generic helpers too. Let's say I wanted to use HashiCorp's retriable HTTP, which retries your HTTP if it fails with certain error codes, right? So now I'm going through a general helper. The retriable HTTP doesn't know where I'm calling to, but the getgolang.org function did, right? And eventually, retriable HTTP gets down to HTTP client .do, which is our other interesting function. So if we zoom out here from this code, right, we have a code call chain that looks kind of like this. Main calls getgolang.org, which calls through get, which calls through do, which calls through do. Do. And the question here is, where in this call chain do we put our annotation? It'll be really weird if we could solve this problem by marking retriable client as an interesting call, but then we have to sort of find all of the possible libraries that could exist. You could make your own helpers that are more generic. But here, really, the place where it stops getting specific is in here, in getgolang.org, because we targeted a specific URL to go to. So if I add an annotation here that says I'm going to golang.org, all right, now this edge, the arrow down, is marked, and so we know where we're going. So to zoom out and give a different example here's a little bit more complicated fictional example, right? We could have main calling main helper, which calls a network of functions. So let's say we started trying to mark up this path, right? We'll start with function A. Our goal is to mark all the paths from main to http.get, so we know why we're taking that path, right? This is not quite like, if there's a bridge out ahead, you want to make sure you've posted signs at all the roads going to the bridge. You don't have to keep marking a sign once you've covered that path. So let's cover func A. So let's say we mark the first one, the first call to HTTP get, and then func A calls func C, which calls get. Let's mark that too. We don't need to also mark inside func C. Maybe func C is more generic. And because we've marked all of the outgoing calls from A, then we've covered the edges into A from main helper rather. So let's mark C, the direct call, and let's mark B. And now all the usage of main helper that gets to interesting calls is done, right? So we have full knowledge about where main helper is calling. So we're good from main, and if we just mark the other outgoing edge from main, then main is all set. So this is the notion that we're trying to build up, is to annotate this call graph. Doesn't have to be all the way down, but we want to make sure that all our paths from main to the destinations are covered. D we don't care about because it's not calling HTTP GET, and funky never got called by main, so we don't care that it's not marked. So in trying to figure this out, I did some exploration. I did what maybe any Gopher would do. I went to Godoc and searched for call graph. And there's a few things that showed up. I got these. These were like 4 of the top 5 results. I think the other one is a fork of one of these repos. Well, this looks promising. So I went looking into this Go call graph area, and I found that all of these packages, they all make call graphs, and they all generate a call graph from the data structure from the top level thing. I've added pointer here, which is not under the call graph tree, but is also related. I'm not sure why it escaped up, but it did. And these 4 all have something else in common too. They all take this SSA stuff. I didn't know what this SSA stuff was yet. We'll get back to that. And so all of these repos are in, all of these packages are in a repo, golang.org x tools. X is like the extended repos. So I looked to see what else was in there. Well, there's a lot of stuff in there. You probably can't read this, and you shouldn't need to, but the first 2 columns all start with analysis. That seemed interesting. I went to look at the analysis package, which defines the interface between a modular static analysis and an analysis driver program. I said, that sounds cool. That sounds like a cool tool I should use. Analysis seems to have come from like a refactoring of GoVet, the different things that GoVet did, and trying to make them into a more modular interface. In particular, analysis has this term of a pass. So if you have an analyzer and you run it on a package, that's called a pass. And it also, I noticed that in these subpackages, there are a bunch of reusable passes. There's one called inspect that produces an inspector. There's a thing called control flow that produces a control flow graph, not a config, control flow graph. This uses inspector, so the passes can use each other. And then finally, for dramatic effect, I found build SSA, which builds some SSA stuff. Well, I needed that SSA stuff, so it looked like a square peg and a square hole. So the plan clearly would be that for each package pass, I want to grab the SSA result from build SSA. I'm going to build the call graph using one of these analyze functions. I picked RTA because it seemed to, again, like fit the square peg and the other ones were rectangular or something like that. And then we traverse the call graph, and we're going to mark these paths leading to the interesting calls. So we also want to report these unmarked paths as linter errors, right? So that if I'm doing a pre-check for a PR or something like that, right, I can assert that everybody's marked all their paths so that the list is accurate. I can use this as a PR status check or something like that. And if everything is marked, I can then report those destination markers as dependency data. Then we can use that to build our graph and so on, right? In particular, for most of the rest of the talk here, we're not really going to talk. I'll come back to that. Change of plan. So here's where I'm going to jump into the primer. A show of hands from here, real quick. Who here feels familiar with the concept of an AST? Okay, a lot of people. Cool. So I won't go super slow there. So for the outline here, I want to go over a bit of an overview of in the standard library, the packages that start with Go/, and then we'll talk about some packages inside xtools Go. In particular, I'm not going to talk about everything, but just some concepts that evaded me. When I got into this stuff, I was looking for a lot of, can I put the square peg with the square hole and the round peg with the round hole, and how do you match up the types? There's a lot of stuff in here, so it can be kind of confusing. The things in Go, there's actually a decent introduction. It's long, but it's decent at the types tutorial here that you can find linked from one of the Go docs. And it talks about the packages in this order. You'll notice they're not in alphabetical order. These are in sort of high level to low level order. And in particular, we can talk about how they fit together. So you have a main.go, which is bytes, right? And we're going to put it into the scanner. The scanner is looking for tokens, right? So these are words or symbols, how you break up how you break up the source file. And then a common technique is to separate the scanner from the parser. So the parser makes sense of the tokens and arranges them and outputs AST nodes, right? Which feed into the type checker, and then constants is kind of hanging out. I don't have a great way of describing it other than to say it's important because constant time evaluation is sort of its own set of language and needs to get evaluated in the compiler. So if you're going to use these things, I certainly ended up using the token and the AST package a lot, parser a little bit. So the most important thing about token is kind of how you use the file sets. In particular, token has these notions of a pause and a position. You notice a pause is just an int. And so what can I do with that? Not very much. You usually want to talk about a position if you want to talk to a human about something. And the pause is more of an internal representation. And the pause refers to a location in a file set. So let's say we're parsing a file a.go, right? In the file set, it's going to exist at certain offsets, these byte offsets. So file A, let's say, starts from 1 and has size 98. We can when we add another file B in, it sort of picks up where the other one left off with sort of a space for the end of file. And so you can use this pause to index into sort of anywhere in the file set of tokens. In particular, the file set is used a lot by the parsers and scanners, and they'll be adding things to the file set as you scan along. And you can't really, like I said, do a whole lot with the pause, but most things that you encounter here, most nodes have a pause, and then you need to get the position using the file set, right? Because the file set knows, well, pause number 50 is in file A, and it can do that lookup. It keeps some lookup tables of, this pause is in this file and stuff like that. So this is a common pattern. You can make a new token file set using new file set. We'll look really quickly at some AST stuff, but since most people mentioned they're familiar with it, AST is abstract syntax tree, and we can do some really easy stuff with the token library and the token package and the parser package to parse a file. It doesn't have to be a file on disk, contrary to the name. And you can use the AST package to print out what you get. So as an example, if I have a func main with just answer equals 42, because that is the answer, you'll get something that looks a lot like this. I won't go through and read everything, but it's interesting to look at these sometimes because it reminds you what Go can do and what its features are, right? So you have an assignment statement and you have the left-hand side and the right-hand side. You can see what token was used to make the assignment. There's a few interesting things, right? We have a basic literal down at the bottom, which is a string, right? It's not converted into a number yet at this point in the parsing. Also, these left-hand sides are lists and right-hand sides are lists of expressions because you can do like simultaneous assignment in parallel. GoAST has a lot of packages under it, or a lot of structs in it for all the parts of the Go language. And if you look at the spec, right, a lot of the terms will match up, and you'll see it sort of makes sense there. A lot of them, you have to cast the interfaces down. These interfaces don't have very much in them, so you'll get something back that is a declaration, and you need to often type switch on it to figure out is a function declaration or is it a variable declaration, things like that. Real quickly about Go Parser. Go Parser has, the simplest one is parse expression. I didn't use that in my example because assignment is not an expression. Unlike in other languages, assignment is very specifically just a statement. So you can parse really simple things with this, but not much else. You can use parse file, which lets you parse either a file on disk or a file supplied by a string or a byte or an I/O reader. They use empty interface here to sort of let everything come through. And in particular, this is the first time we're sort of seeing this mode pop up. A lot of the parsers and the scanners have a mode in which they operate, and you need to pick which parts of functionality you want. You get back an AST file from this if you succeed. There's a similar function, parse expression from, which takes the same arguments and gives you an expression instead. Parse dir is in here too, but I don't recommend you use that. I recommend you use Go packages in the xtools, which is a newish library. It was talked about yesterday in one of the sessions in the morning. This replaces Go Loader, if you used to see that. This is now deprecated, I believe, as of this summer, so fairly recently. And it's definitely a nice interface to use. It's a little bit more verbose in some places, but you just need to give a config, and then you load these patterns that look like the patterns you give to Go Build or Go List. So you can do like dot/triple dot. You can give relative paths. You can give URL package names, things like that. We talked about SSA before, and SSA will come up again here. SSA is in particular means static single assignment. It's just an intermediate representation that the compiler can transform things into, and it allows for some better analysis of what your code is doing. That's why a lot of these analyses build an SSA program first and then analyze that. It's single assignment, so you only assign to something once. You can tell very quickly where it's used and where it isn't. This package has a big warning at the top that says the interface is experimental and likely to change. So I transfer that warning to you, and now we can move on. In particular, this package has a lot of documentation, and when I first read it, I skipped past it real fast, and I was very confused for a while. And then I figured out that the primary interfaces of this package are member, value, instruction, and a node, which could be a value or an instruction or both. This is listed literally in the documentation that I skipped past. So I recommend you at least start reading from where you see this in the Go doc, and then it all kind of makes sense. A lot of these structs in the Go doc, and for some of these other packages too, if you look at a particular struct, they implement all these methods and there's no documentation on them. All the documentation is on these interfaces that they're implementing. So it's a little hard to know where to look for some of these things. In particular, also, you probably want to look at SSA util, which is under this package, or in terms of the hierarchy, which has builder and helper functions. You can kind of piece together how to build an SSA program using just SSA, but you don't want to. Use SSA util. That's where kind of the stuff that you want to actually call is. We've been talking about the call graph, and the call graph package is particularly important to what you might want to do if you're analyzing these call patterns, right? The call graph has a graph at the top. There's a root node, and in particular, there's also a map from SSA function to node, and they're one-to-one, like that. A node looks like a function. It has an ID, which is just an artificial counter, a synthetic counter, and it has edges in and edges out. And an edge looks like a caller calling a callee. Unfortunately, they're very close to each other on the keyboard and look very similar. But a caller calls a callee, and they might do it at an instruction site. Most code that you write will have a call instruction site. If it's synthetic code that Go is generating for you, this call instruction may be nil. So just be aware of that, or you'll find that out pretty quickly. Let's see. So what this looks like in practice is we might have one node for func A. It might call function B multiple times, right? So there's multiple outgoing edges to B, right? But there's only one node B. And there's one going out to C also. In particular, another advice that I could give to you would be to play with this tool, which is in a slightly different directory. All the commands, the executables that you can build in Golang X tools are in the command subdirectory. This will let you generate call graphs for any program you want to run it on, and you can run all the different analyses. So it's good as a double check also to say, hey, did I do this right? And it's also very good for examples. It shows you how you can build one of these yourself. So I highly recommend this. In particular, when you're also traversing call graphs, remember recursion. Recursion is a thing. So maps, which sometimes in other languages is pronounced set, are useful here, maps of nodes or maps of edges that store where you've been already. This is also a common technique that seems to pop up. And lastly, in the primer, talking about analysis, we talked a little bit about this before, but we'll go into a little bit more detail. So we have an analyzer, which does a particular form of analysis, right? We have different packages, so each of these is a pass. We mentioned that name before. And there's two other things that are interesting you can do here. You can store a fact, and a fact for an analysis is the same analyzer storing information about a package it's already seen. Right? You can store this stuff for later. You can store a fact about an object, or you can store a fact about a package in general. You can also return results. And so this is how you talk horizontally. One analyzer can use the result of another analyzer. So we talked before about the control flow analyzer uses the result of the inspector analyzer. So you can't read facts of someone else's analyzer, and yeah, so that one goes that way, that one goes that way. Yeah, so we're out of the primer. Thanks for sticking with me. let's talk about attempt number 1. So the plan, just to reiterate, for each package pass, we want to grab the SSA result. We're going to build the call graph using RTA Analyze. We're going to traverse the call graph, recording those facts, and I'll use the word facts since you've heard about it, to mark these paths that lead to the interesting calls. We want to report unmarked paths as errors, and we want to report the destination markers. So there were some bumps in the code. If you start building your analyzer from scratch like I did, you may hit some of these bumps. The first is if you don't declare facts, then you don't get any of these dependency tree behaviors. It won't bubble up from the bottom, which is what I really wanted. I wanted to start from the bottom and start from the interesting calls and move up and mark those paths sort of from the bottom up. Yeah, I had to read the code to figure this out. I didn't find documentation about this. You won't get, the pass in particular also gives you some syntactic analysis. The AST stuff we talked about before, it's sort of already done for you, and they give it to you, but if you don't declare facts, you won't get all of the syntax that you wanted. Build SSA also isn't modular, and I put modular in quotes here because modular is a term from the analysis package, where this is where facts bubble up. That's what they call a modular analyzer. Each pass builds a new SSA program. There's a comment that says, we couldn't do this because the API didn't let us do it. I thought I was saving time by using these build SSA things, and it may not have been such a savings. Build SSA also hardcodes builder mode 0. There's a comment there also that seems prescient that says, someone else might need some other mode. We'll talk about it someday. So you may need this, you may not. Just be aware of it. So I started writing my program and I got my facts working and I was analyzing these call graphs and I wanted to use another part of analysis which seems really cool, this single checker library, which gives you singlechecker.main, which parses command line flags for you so you don't have to figure out which packages are going to be analyzed, things like that. So I remember I wanted to do my linting to find errors, and if there were no errors, I want to report the results successfully. So here's my example. I might call my analyzer from singlechecker.main, that's all you have to do. And then maybe I want to report the results. There's a problem here. Does anybody spot it? Yeah, singlechecker main doesn't return. It calls OS exit, which messes with me. So the reporting of results never happens. And because it calls OS exit, like it's not even panicking, I can't even defer my thing because OS exit just says, nope, exit right now. So this kind of got in the way. But I tried some workarounds. So if you can't do something at cleanup, well, I know that I'm done when I get all the way up to main, right? So I can just check for if package equals main. Well, there's multiple packages named main. They're built in different ways, so you might have the test main, you might have main with, I couldn't figure them out. There's 3 or 4 of them. They're interesting. So if I can't do this, well, I could do some writing to standard out or to a file. The package, the single checker driver makes the analysis happen in parallel, so you have to make sure you do this in a sort of locked way or something like that. But you also have this main, right, that you can't really, well, what if you want to do something different? There's either single checker main or there's your main. Well, I guess then we got to run the analysis driver in a child process, right, if you can't communicate with it. And I figured out a funny hack to, like, via an environment variable, either run their main or run my main, and it sort of looks like fork exec, right? These were all workarounds, and they worked. I was getting stuff out, but even that stuff wasn't working very well. I had these multiple passes, and they were each with these separate SSA program builds. I think that was part of the problem, as they weren't able to sort of cross over the package boundaries. The builder mode might have been messing with me. I didn't do a controlled experiment here, so I don't really know what was going wrong. There's also some limitations on the rapid type analysis package. It's less precise than this pointer package, but the algorithm is a lot faster. This is from the documentation in RTA. I said, well, I would like some accuracy, so I guess maybe let's go with the pointer analysis, because you just told me it was going to do a better job. So attempt 2, I want to rebuild from the ground up. So I'm going to swap out RTA for Anderson's pointer analysis. This is another package that has a giant technical specification in Godot. So it looks very impressive, so I'm on board with that. I wanted to start with a simpler driver, so I went back to basics. So we went back to Go, the Xgo packages, Xtools Go packages, which has that load. SSA util has an all packages that consumes the package there, another square peg to the square hole thing. And you do have to remember to build your SSA program once you sort of set it up. The programs can sort of accumulate code, and then you can do the build. If you don't do the build, you'll get funny errors. And then I'm going to call pointer.analyze. This is the pointer library, not like just a pointer. So again, this stuff, oh right, and then we're going to visualize the call graph. And this time around, I tried to skip some of that linting error stuff and reporting the dependency marker stuff. It's sort of, that's really the easy part, right? I can just, once I've accumulated this data, printfing in a loop, that's not hard. And analysis pass has a built-in API called reportf to report the errors. That's not the hard thing either, right? So I wanted to minimize my dependency on the analysis pass to try to figure out, to try to just focus on, can we mark these things correctly? Can we get through it, right? So does it work? Well, I got this. So that's not all of it. This is still not all of it, but it looks pretty. It's kind of like this abstract, city skyline kind of thing. That's the top of it. I had to turn it so you could see more of it because there's 4,000 lines in there. Yeah. So I started going through this call graph that I had produced with my better visualizer. It did help a lot, and it highlighted some things that, in retrospect, some of them should be obvious. But it sort of reminds you like, oh yeah, Go has to do that. Most of what I'm going to talk about here is specific to Unix/Mac, Unix style things. I was running this on a MacBook, and I didn't run it on Windows. I'm sure you'd see a different sort of results. Opening files is common. OS.init, it opens some files. Standard in and standard out and standard error, right? Those are not IPC calls, right? So, but they'll show up if you're looking for all the uses of OS file, right? Let's see if you can guess this one. Crypto dev reader, crypto rand dev reader reads from WRandom, right? And I won't make you guess the last one, but the net package in its machinery is reading a lot of stuff that makes sense again. It's figuring out how to resolve DNS names and what it should do about ports and things like that. I also got a couple of false positives because in particular, these call graph analyses don't really follow the execution of your code. They look for assignments and sort of shuttling the function pointers around. Or this is how I envision it anyway. That may be slightly inaccurate. So let's take this small example. So I have parser.parsefile, which we used before. I made a new token file set. The empty string is an optional file name that I don't care about here. So this is the tiniest program I could make, right? Package main. There's nothing in it. Great. So we're going to analyze it. And so the analysis is going to look through, and we're going to look in parsefile. And parsefile calls readSource, which is a private method inside the parser package. And resource looks at the source interface, right? And remember, parsefile can either look at a file or it can look at like a string or a bytes that you gave it. So this is excerpted, but there's a if source equals nil, and then it tries to convert everything to a byte. And if you didn't get any of that stuff, then you go down to the bottom and you use IOUtil read file on the file name. So because it's not actually looking at the flow of the calls through here, it looks like read source uses a file. And it looks like parse file uses a file. So that example that we looked at, which clearly does not use a file, is marked as calling os.open, right? So that's not exactly what I want. The third one, which I think is also super interesting, so I'll give it really big fonts, is the sync once do problem. This is not specific to sync once do. This could happen to any of us, anywhere, at any time. So a cautionary tale. What does sync once do? Sync once do calls function f once, ever, right? It guards, right? It guards this function. And this thing will only happen once. So what do you have? You have things like net lookup protocol. So it's going to read that protocol file from before once. So that calls sync once do, which calls net read protocols. And both RTA and pointer analysis seem to be fine with following this through, right? And we have, say, resolver config, which also calls once on its init function, right? And you have syscall.getenv, which copies the environment when you start up once, like the first time you get the environment. This last one in particular is interesting. Yeah, it's interesting. So just a refresher, right? We talked about the call graph before, and these are the data structures involved. In particular, looking at the graph, right, there is a one-to-one mapping between an SSA function and a node. There's only one node per function. So really this graph looks like this graph. And this is particularly a problem because syscall.getenv is part of os.getenv. And so if everybody calling sync once do appears to call all the stuff on the right-hand side, then everybody is using everybody else's stuff. So anybody who calls os.getenv appears to be initializing resolve.conf or something like that, right? And those things probably also call os.getenv somewhere in there. So now you have this like funny loop thing, and it's just weird. But we know how to do this, right? If you look at the code, right, we know that lookup protocol was trying to call read protocols. So we can go back and we can just sort of redraw that edge. You need to do a little bit of fiddling because these things aren't always pure functions. Sometimes they're bound to a struct. Sometimes they're anonymous functions, things like that. But we can do the same for the other ones, and then really what we have is a graph that looks a little bit more sane. I think my helper for this is called unravel sync once do. So now we have a graph that looks sane. And the first graph that I showed you, a lot of the stuff in there that you probably couldn't read was os.getenv, which didn't make any sense. So does it work now? Well, pretty much, yeah. This is my output on my test program that has a bunch of different ways to pass function pointers and return anonymous functions and things like that. I colored everything red when it was unmarked, and things are bold when we get down to the interesting functions. And so if I start marking up things with those comments, right, then I can add a little bit of an annotation here, and we get a green check mark going through. So here I didn't annotate the OS opens, and I did annotate the HTTP gets. So we can see that we have some work to do. So you can see where this would naturally flow into collecting all those things in pink, the golang.orgs, and also reporting the red X's. So now you got to run on real code, right? I ran that on a test function. You know, you can only get so far with toy code. It seems like it was going to work. Yep. Yeah, you probably saw this coming. In particular, my team owns a microservice framework that's local to us, and I use some reflection in there to make things easy for the user. We also use a command line parser in some places. I like this command line parser personally, and it seems to use reflection in certain places. So there's certain calls that were just sort of not getting to the place where they were really calling. I would run the analysis, and I said, look, I got some great results. And I turned to my colleague, and they said, right, but like, aren't we using Redis there? Why isn't Redis on the graph? That's how I found that stuff. And you could have expected this. Maybe rapid type analysis has a comment right up front that says, we do not include edges for calls made via reflection. And pointer analysis is something similar. Some things are supported. I'm not sure what's supported, so I'm not quite sure. Yeah. So my takeaways here are that call graphs can be easy, or they can get tricky pretty fast. If you're analyzing a pretty simple program, I think you can get a lot out of them pretty quickly. But the more you complicate things and the more frameworks you're trying to use, you may get stuck a little bit. Some documentation is great. Some documentation probably could use some help. And I learned a lot about what makes good GoDoc, for instance. I don't know that GoDoc is always the answer to things. It gives you, it lists out the classes and the functions in alphabetical order, which isn't importance order. And so things that are important can be hidden. And maybe we also need some more readmes and some more tutorials to go along with things like the types tutorial. This could be a place to have people contribute also, I think. Starting simple is good. Starting from basics is good. Really, part of my pitfall in attempt 1 was trying to use all the fancy, shiny parts of analysis pass at once, right? It was too much, too fast, right? This is another thing about GoDoc. I know sometimes my tendency is I read a package and I'm like, oh, look at all I got to use all the methods, right? How many can I use at once? That's not a great way necessarily. You can get a good survey, but it may not be what you need. I think also another takeaway is I could have done a better job at talking to the community about what was going on here. The couple times that I did wander into the Slack channel and ask, hey, has anybody heard about this kind of thing? I asked about the single checker, that it wasn't returning, and hey, does anybody know a different way to work around this? And I had actually looked first for some GitHub issues, and I found them. I found some people had been like, hey, I want this. And when I walked into the Slack channel and said, hey, does anybody know about this? The people who put in those PRs, like in a minute, jumped up and said, yeah, I asked for that. And I was like, okay, here we go. So there's also been some, I would say there's been some amount of people talking about this analysis package and what you can do with it, how it should work lately, at least in my Twitter feed. So I think there's some consensus and some community interaction that would be better here. So yeah, I want to say thanks to all the people who helped me along this way. First to GopherCon for letting me give this talk. It's an honor to be here. It's my sort of second year doing Go, so it's cool to be here. And I want to thank my team in particular. They've given me a lot of support at Bloomberg. And thanks to you for sticking it out. And hope you had a great GopherCon. Thank you.